Hi everybody, I'm Jason, welcome back, and today I'd like to tell you that you have been lied to about imaginary numbers. What I'd really like to do is talk about what I think is one of the biggest misconceptions in all of mathematics, and of course, imaginary numbers. And along with that comes complex numbers. When you take an imaginary number and a real number and you combine them together, you get a complex number. And let me tell you something, we've all been victims of this terrible branding. Calling these numbers imaginary might be the worst marketing decision in the history of mathematics. Now let me take a second and explain exactly what I'm talking about. When I was young and when I was first learning about these imaginary numbers, I really thought, why are we even learning any of this stuff anyway? What is the point if these numbers are imaginary to begin with? And it wasn't until many, many years later that I actually learned that imaginary numbers are really one of the most useful things in all of math, in science, and in engineering, particularly quantum mechanics and physics, which leads to all sorts of modern technology like the transistor, the smartphone, the computer. I could go on and on and on. But here's the thing, when it comes to these things that we call imaginary numbers, there's really nothing imaginary about them at all. Now here's the deal, the mathematicians back in the day, they had to call these numbers something, and they settled on the word imaginary as a label really just to distinguish them from the real numbers that you already know about. For instance, real numbers, 1, 2, 3, 4, 5, right? And also the fractions, 1/2, 1/3, 1/6, all of the decimals that you know about, that special number 0, and also the negative numbers, -5, -10, which, just as a reminder, it denotes if you owe something to somebody else. I have -$5 if I owe somebody else $5 that I don't really have. Or maybe I'm measuring below sea level. That could be a negative elevation or altitude below sea level. Or I could say a negative temperature, which means just below the 0 point on the temperature scale. So it's really unfortunate that they chose the label imaginary, but just keep in mind that the only reason they did that is to distinguish them from all of the real numbers that you know about already. Now here is the punchline of really what I want you to remember from any of this, and that is that imaginary numbers are as real and as useful as any other mathematical tool that we have at our disposal. In fact, they're absolutely crucial to understanding the universe, and by the end of this video, I want you to understand exactly why. Now first, let's back up the truck a little bit and let's start with the origin of these numbers, these imaginary numbers. So back in the 16th century, Italian mathematicians were wrestling with cubic equations. Remember, equations have variables, placeholders for numbers. You might have x as a variable, y as a variable, a or b, and actually equations can have more than one variable. Now, cubic equations are variables that have an exponent of 3. Now, I want you to remember for a second that a square, what we call a square in math, that is a variable or a term that has an exponent of 2. So a cube has an exponent of 3, and mathematicians were wrestling with equations which had cubic terms. Now, particularly a brilliant mathematician by the name of Girolamo Cardano was trying to solve equations that seemed impossible at the time. So when he was solving these cubic equations, he kept running into the square root of the negative numbers running around his equations. And that was something that was considered nonsensical or sort of insolvable or unsolvable at the time. So the bottom line is that in order to solve these equations that had the square roots of negative numbers, he had to invent a new number called the imaginary number I. So we'll get to that in a second, but for now, let's just review a little bit about square roots. So a square root, for instance, of the number 16 is 4, because 4 times 4 is 16. So when you're finding the square root, all you're trying to do is to find a number so that when you multiply that number times itself, you get whatever is under the square root symbol. So square root of 16 is 4 because 4 times 4 is 16. But the square root of 4 is actually equal to 2. Why? Because 2 times 2 is 4. Now the square root of 1 is the easiest one of all because that's equal to 1. The square root of 1 is 1 because why? 1 times 1 is equal to 1. So here you go. What is the square root of -4? That's what he was running into. How do you do that? Well, the problem is when you multiply numbers together, especially if it's the same integer, you're always going to get a positive number. You're never going to get a -4. The square root of -4 can't be 2 because 2 times 2 is 4, not -4. So that doesn't work. The square root of -4, it can't be -2 because -2 times -2, remember it has to be the same thing multiplied by itself, that also gives you a +4. So the square root of -4 doesn't appear to have any answer at all according to the rules of math of the day, and so he was having problems solving these equations. So basically what he did is instead of giving up, Cardano did something revolutionary. He actually said, what if we just pretend, and I'm quite serious, he said, let's pretend that these numbers actually exist. And so when you do that, you invent a new symbol for the type of number that up until then you've never used or worked with. And so at that point, you could say the solutions started working. It was like discovering a new color, for lack of a better word, that helped you see the whole rainbow better. So the square root of -4 isn't 2, and the square root of -4 is not -2. What Cardano said is that the square root of -4 is 2 times this imaginary number I, and we use the letter I to denote it. 2 times I, and I, the letter I in algebra and in math and in calculus, is defined to be the square root of -1. So we basically say we really don't know how to take the square root of a negative number and get a real countable number, so we invent a new number called I. And so that when you take the square root of -4, you get the number 2 that you would kind of expect to get, but you slap an I at the end so that that represents the square root of -1 and takes care of the negative sign that you have a problem with. So the square root of -100, as another example, is not 10, it's 10 times I, because I, again being the square root of -1, takes care of the negative sign. The square root of -16 is 4 times I. The square root of -64 would similarly be 8 times I. So every time you take the square root of a negative number, you get the number that you would expect if there was no negative sign there, but you would have that imaginary number I sitting at the end of it, multiplying times the answer. Now, before we go too much farther, before you kind of like think this is kind of silly to even do this, you got to remember that when you were born, you were taught about all the numbers. But as humanity learned more and more math, all of these kinds of numbers that we take for granted had all have to be invented. First, you start with the countable objects. 1 apple, 2 apples, 3 apples, 4 apples. That's the whole numbers, right? But then you realize you can have half of an apple. And so you can have halves, and you can have thirds, and you can have fourths. And then you realize that those fractions can also be represented by a decimal, 3.5, 3.75, and that these decimals can then also repeat, and they can go forever. 3.33333333 repeating. Those are all different classes of numbers that had to be invented. Then the concept of 0 was a number that was invented. It seems silly to have a number that represents nothing, but we all know how important 0 is. Even in just writing numbers down, 0 is a placeholder for the place value, right? And then you have the negative numbers. And that personally was very difficult for me to understand in the early part of my education. I didn't understand, but we now know the negative numbers represent a deficit or below the 0 value on a temperature scale, etc. I've given the examples of that already. So when you look at it in the broader context, inventing a new imaginary number I to handle the solutions of these equations doesn't seem like such a crazy idea after all. Now I want to share with you the main punchline about what makes imaginary numbers really so useful and so important. And I really wish somebody had told me this in the beginning when I was learning about it. It is true that imaginary numbers are not countable. You don't count them on your fingers. They don't exist on the same number line as all of the other numbers we talked about. That is true. However, when you combine different imaginary numbers together through multiplication, they turn back into real numbers. And that is what makes them, in my opinion, so useful. Right? I'm going to say that one more time. If you have an imaginary number like 5i, and then you have another imaginary number like 6i, individually, they're both not countable. They don't represent something on the real number line. But if you multiply those numbers together, then you actually get a real number back that is no longer imaginary. right? So the reason that this happens is when you go through the rules of square roots and multiplying them. Remember, the number I is defined to be the square root of -1. And I'm going to show you on the board exactly why you multiply I times another number I, you get I squared. And so when you have that square root of -1 times another square root of -1, the way square roots work, what you actually get at the answer is -1. Not an imaginary number, a negative number, but still a number that is on the real number line. So when you take 5i times 10i or 16i times 17i, the i's get multiplied together and they sort of disappear, and the answer that you get is no longer imaginary. So a lot of times in math, you end up with imaginary answers as intermediate results, but when you combine it with other equations, they turn back into real numbers. That, in my opinion, is why they're so useful. I kind of want you to think about two mirrors at a 90-degree angle. So this is like a 90-degree angle. Imagine them appearing in front of you as like a corner, right? Now, imagine yourself throwing a ball at the first mirror, so that it bounces to the second mirror and then it bounces back towards you. Or you can imagine shining a laser. The laser goes and bounces off the first mirror, bounces to the next mirror over, and then comes back to you. As the mirror leaves your location and as the photon or the ball leaves your location and interacts with the first mirror and bounces, you could sort of say that it's over there and it's in the imaginary realm or the imaginary domain. When you have it in your possession, it's like a real object that's countable. When it leaves your hand, it's kind of in another domain. Just use the analogy here. It's a loose analogy. It bounces off that first mirror and it goes horizontal and it interacts with the second mirror. And again, it's not in your possession, but it goes through two interactions with two of these imaginary number mirrors. That's kind of what they're representing, and it bounces back towards you. And when it comes back to you and you catch it again, it becomes real again. So what we do a lot of times in math is we go and we solve the problems in the imaginary number domain and we form manipulations over there. And then when we turn it back into the real number domain, we get the answers that we can count. I can go into many, many, many examples. When you deal with Fourier series, Fourier transform in engineering and signal analysis, you transform the problem into sort of an imaginary number domain. And the rules of the math over there in that domain can be simpler, but they involve imaginary numbers. So you do the calculations over there involving imaginary numbers, which is simpler than doing them with real numbers. But then when you're done, you convert it back, or you do an inverse transform and convert it back to the real numbers. And then what you've done is you've simplified everything, but you had to use imaginary numbers to go round robin and get your real answer back. So imaginary numbers may not be real numbers, but they are absolutely critical for any modern problem in science and engineering. So I'd like to talk for just a second about some applications that actually rely on imaginary numbers in terms of how we calculate things with them. First, let me ask you, have you ever used electricity? Well, actually, imaginary numbers are critical for understanding alternating current, AC, which is electric current. So those smooth sinusoidal waves that are actually oscillating voltage and current in your home or in your workplace, those are modeled by complex numbers. And the complex number, remember, has a real part and also an imaginary part. Now, as an engineer, most of the time when you're doing calculations with any kind of sinusoidal like AC oscillation, you're almost always using imaginary numbers. In fact, you know about power, electrical power. You've probably heard of watts, right? So when you have a device like a resistor, it's just a real number of watts. But when you have a capacitor in your circuit or an inductor in your circuit and an alternating current source, which is most of the time in circuits, then what we actually do when we actually calculate power, we calculate it as a complex number, which has a real part and an imaginary part with I, right? The real part represents the real amount of watts that is dissipated as heat in your circuit, but the imaginary part of the power, it represents power that's not dissipated, but that's sloshing back and forth between magnetic fields in the inductor, the coil of wire in your circuit, and in the electric field of the capacitor of your circuit. So power can be either dissipated as heat, or it can be oscillating back and forth in electric and magnetic forms in the circuit. And the way we bookkeep all that is the real part of the answer, the real number part, is the real dissipated power, but the imaginary part is the power that's sloshing back and forth, but it's not really dissipated as heat. That is critical. You're constantly doing that in the realm of electrical engineering. Let's go a little far out here. Let's talk about quantum mechanics. That, of course, as you know, describes the fundamental behavior between matter and light. And in that realm, imaginary numbers aren't just useful, they're absolutely indispensable. You may have heard of the Schrödinger equation. So that's basically the master equation that governs quantum mechanics. In quantum mechanics, atoms, electrons, photons of light, all these things are governed by a wave function. So instead of a little particle, everything's modeled as a wave. And the Schrödinger equation is the equation that tells us how the waves are changing with time, basically. The wave function itself, which literally models everything in the universe, is a combination of an exponential function with complex numbers or imaginary numbers running around in there. So you really just can't do any quantum mechanics at all without imaginary numbers. That means no transistors, no iPhones, no computers, no memory, nothing, because all of those devices require quantum mechanics to be understood. Let's switch gears. Let's talk about robotics. There's something called control systems. That's sort of the control system theory, is how you get a mechanical system to behave, how you get it to smoothly move between point A and point B without wild oscillations. That's full of imaginary numbers. What about signal processing in your smartphone that processes your voice for transmission? Almost all of it involves imaginary numbers. What about the math behind these noise-canceling headphones that you listen to on the airplane? You guessed it, it involves imaginary numbers. Computer graphics, digital processing of images and movies, complex numbers, imaginary numbers again. Now this is a little bit silly, but calling these numbers imaginary is kind of like calling a smartphone a magic rock. Yeah, sure, it might seem magical if you have no idea how it works, but it's a very, very real thing, a very powerful tool that shapes everything in our modern world. So now that we have a really good overview of what we're talking about, what I'd like to do now is roll up our sleeves and really dive into imaginary numbers in a little more detail so you have a concrete understanding of exactly how they work in a nuts and bolts way. So the punchline here is the following thing. The imaginary number I is equal, by definition, it's defined mathematically to be the square root of -1. Now, I've been telling you since the beginning of talking about radicals that we cannot take square roots of -1, right? So when you first learn about imaginary numbers, first of all, you think they're really, really scary, really, really complicated. But I'm telling you, they're not complicated at all to work with. Just kind of follow along with me. Secondly, you're kind of scratching your head. Why? How can we do that? How is that legal? We can't take the square root of a -1. Well, the truth is you cannot take the square root of a -1 and get a real number back. In other words, all of the numbers that you've ever been exposed to your entire life are what we call real numbers. Those are the numbers that we can kind of hold in our hand, for lack of a better word. Numbers like 2 and 3, even negative numbers like -10, or fractions like 3/4 or 1/2, or even non-repeating decimals like pi. Or like other, there's tons of other ones, like square root of 2 and square root of 3 and things like that. Those have decimals that go on and on forever. Those are all called the real numbers. The truth is you can't take the square root of a negative number and get an answer that's a real number. So mathematicians over the years have invented a totally new kind of number. It's called an imaginary number. It's a terrible name because it makes it sound like it's a fictitious thing that's useless. The truth is it's very, very useful. And we define the letter I, we're going to use it as a placeholder, to be the square root of -1. Now it is true, I cannot find a real number that will multiply by itself. Like we say the square root of 9 is 3 because 3 times 3 is 9. We say the square root of 16 is 4 because 4 times 4 is 16. We can't say that the square root of -1 is some number times some number because there is no number that does that. We have to invent something else. It's called an imaginary number. You're going to have to get used to seeing the letter I running around. When we're simplifying expressions, you can kind of think of I as like a variable. You can combine terms, like terms. We have to have I involved and so on. We're going to be squaring and cubing and dividing and multiplying by I. We're going to be doing all the same things we do with all variables and numbers all the time. But in the back of your mind, anytime you see the letter I anywhere on a paper in math, you need to remember that that is the square root of a negative number, or the square root of -1, right? And it's defined like that. Defined like that as a definition. This is not something that you discover under a rock somewhere. It's something that's mathematically defined. The reason is because it's useful. Imaginary numbers, we will see, are very, very useful. All right, if you define the letter I, this imaginary number, to be the square root of -1, it's not a real number that this is an imaginary number, right? Then because of that, we can say the following thing. Thus, if you square both sides of this, if I square this and square this, then we also know that I squared is equal to -1. How? Because if I square this, I'll get the I squared. If I square this, they'll cancel with the square roots, and then I'll have a -1 back. So this is equally important as this. So I'm going to circle this, and we're going to reference it throughout the lesson. It's so important. I want you to stop for a second and absorb this. It looks, and it is, very simple, but there's a lot of depth into what's on the board here that we're going to see as we work through the problems. Anytime you have the square root of -1, of course it's I, but the concept of I allows us to take the square root of any negative number we want, but we're going to get I somewhere in the answer. And because of that, anytime you square I, you get back a real number, which happens to be -1. It turns out this property right here is the secret sauce as to why they're so useful. And I'll give you a little bit of a preview. Imaginary numbers are not something you can hold in your hand, right? But if I have an imaginary number in this hand, and I have an imaginary number in this hand, oftentimes if I combine them together, in this case, what's written on the board is by multiplying them. I have an imaginary thing times an imaginary thing, which are not things I can hold because they're imaginary numbers, but when I multiply them together, I don't have an imaginary number anymore. I have a real number back. This -1 is just a -1. It's a real number. And that is probably one of the biggest punchlines as to why imaginary numbers are useful. Because I can work with imaginary numbers over here, and I can work with imaginary numbers over here, neither one of which represent real numbers, but I can combine them together, and often my equations will combine them together. So poof, they're not imaginary anymore, they're real. So that's actually one of the reasons why they're so useful. So this is the punchline, and I want to leave it on the board, and I want to motivate why we actually need imaginary numbers. It turns out that all of the equations we've learned how to solve, all up until now in algebra, have required different kind of numbers. Now, there's a little bit of history of mathematics here, a little bit, okay? Some equations require positive numbers to solve. Some equations require negative numbers to solve. Some equations require fractions to solve. Some equations require imaginary numbers to solve, which is what we're going to get to. I want to go down that with you because I think it's very important that you understand where this comes from. So I'm going to talk about real numbers for a second, because real numbers, let me see if I can write real numbers down. Real numbers are the numbers that you've been exposed to your whole life, all the way from, first grade all the way up until now. Real numbers, every number you've ever seen, even if it was negative, is still a real number. Even if it's a decimal, is still a real number. They're all real numbers, right? So all the equations that you've ever learned how to solve only required real numbers to solve them. But there are different types of real numbers. So let's talk about a few of those, right? Let's take a couple of equations, right? Let's take a very simple equation. Let's say we have the equation x plus the number 1 is equal to 3. You all know how to solve that equation. You just move the 1 over by subtraction. 3 minus 1 is 2, so what we found here is that x is equal to 2. Now, what kind of number is 2? Well, it's a real number. Of course, it's a real number. What kind of number is it? It's a real number. I'll put that down. But it's a positive number. So that's a type of number that was invented a long time ago to solve certain kinds of equations. Equations that look like this. Something plus 1 is equal to a number where a positive number is the value of the variable. So we needed a positive real number to solve that type of equation. Let's pick another kind of equation. Let's say we have x plus the number 2 is equal to 1. Well, this looks the same, but if we solve it, it's slightly different. If we subtract 2, then we'll find out that x is not equal to a positive number. X is equal to, not -2, of course, x is equal to -1, right? Because -1 plus 2, of course, will give me the 1. Now, this is also a real number. Negative numbers are real as well. However, this one's slightly different. It's a negative number. Now, I need you to think back to maybe 1,000 years ago or 2,000 years ago when algebra and mathematics were really first start to be solidified, right? The idea of a positive number is easy to understand. I have 5 eggs in my hand, easy to understand. I have 16 buckets of rocks or whatever. I have 16 pencils. That's easy to understand. Positive numbers are easy. But at some point in history, somebody must have thought, hey, the idea of a negative number is useful too. It sounds crazy to you because you're so used to dealing with negative numbers. But there was a time when nobody knew what a negative number was. Somebody had to invent the idea of a negative number. Why? In order to solve an equation like this. When I subtract something bigger from something smaller, then I can't use a positive number. I have to introduce the idea of kind of owing somebody. I always say negative numbers is like if I owe you something. So if I get an answer of x is equal to -1, it doesn't mean I have $1 in my bank. It means I'm bookkeeping that I actually owe you $1. So I don't have that dollar, I actually owe it to somebody else. That's the idea of what a negative number is. But that number was not something that we're born understanding. You have to be taught that. And it's a useful idea to solve an equation like this, which is a different kind of equation, right? It requires negative numbers as an answer, or we need to invent this in order to solve this kind of equation. So let's continue on. Let's take another kind of equation. A little bit down the way in history, somebody tried to solve an equation like this. X plus 1/4 is equal to 1/2. You all know how to solve this, no problem. I'll just subtract the 1/4 from both sides. What am I going to get? I'm going to say that x is equal to, well, if I take 1/2 minus 1/4, of course you can do the common denominator, but you all know 1/2 minus 1/4 is equal to 1/4. Right? Again, this is a real number. I can have 1/4 of a sandwich. I can have 1/4 of a candy bar. Of course, it's a real number. And it's a positive number also, right? I'm not writing down every little attribute of all these numbers. It's a positive number just like this 2 is. However, it's different than the others because we call this rational. A rational number, remember, is a number that can be written as a fraction, any fraction. So 1/4, of course, is a rational number, but I didn't write it down for these two. These two are also rational numbers because 2 can be written as 2/1. That's a fraction. -1 can be written as -1/1. So that's a fraction. So let's take a little bit of an aside to talk about these rational. I'm going to give you some examples, some more rational numbers. The number 10 is a rational number because I can write it as 10/1. The number 3/7 is a rational number because it's a fraction, of course. The number -2/3, that's a rational number because that obviously is a fraction. It happens to be negative as well, but that's fine. It's still rational. Let's take something crazy. 1028 divided by 37. That's a fraction because it's a crazy numerator and a crazy denominator. Let's keep on going because we can make up a few more, and there's a point to this, I'll promise. Let's take a look at 0.75. You might say, well, that's not a fraction. However, you know you can write this as 3/4. That's a fraction. So this decimal is disguised. It's a rational number too. And it turns out that other decimals are rational. For instance, 2.125. Any decimal that terminates, any decimal that terminates like this, that can also always be written as a fraction. So this is a rational number too. I can go find a fraction that's equal to this, right? Let's take our last crazy one. What about that's not an equal sign there, sorry about that. -2.1414, but I'm gonna put a repeating bar over the last 14. So this is 2.14141414141414 goes on forever. As long as you have a repeating pattern in your decimal, you may have learned this in previous lessons in algebra or in other math classes. As long as it's some sort of repeating pattern, then it's always rational. I can find a fraction that's equal to this, even though the decimal goes on to infinity. As long as it is repeating like this, I can find a fraction that's equal to that. All right, so I'm going to write down this is a repeating decimal. Let's put the G here. Decimal. Why am I going through all this stuff? Because all of these, every one of these things, pretty much every number that you've really been exposed to up until now has been a real number and it's been a rational number. So these are all rational, right? But the point is that throughout history, first we didn't need to know about fractions. At some point in time, there was some person that decided that it was useful to know what a half of a loaf of bread was and represent it as 1/2. Right? Or 3/4 of a dollar is worth something. So somebody had to invent fractions, but these different types of numbers that we've used have all been invented to solve different kinds of equations. This one requires real positive numbers. This one requires real negative numbers. This one requires real rational numbers. And then once we figure that out, we realize these are also rational numbers too. But then a long time ago, probably the ancient Greeks, I'm not totally sure, but probably the ancient Greeks, figured out that some numbers do not terminate like this. The decimals don't stop. And also, if the decimals go on and on forever, there are some special numbers that don't have any repeating pattern. like this was 141414 on forever. There are some numbers that have infinite decimals, but they don't repeat in any pattern that we know about. And those are useful to solve certain kind of equations as well. So the famous equation, the area of a circle is pi times r squared. You know that equation, of course you do. Everybody learns that equation back in 5th or 6th grade, right? But in order to solve this equation, we need to invent a new kind of number, right? So we need, we need pi, right? Which can be approximately written as 3.14159 ... It goes on and on forever, but the pattern of the decimal, this 14159, it never repeats. We have supercomputers calculating pi out to 100,000 million trillion decimal places. There is no pattern to pi. It's called an irrational number because the rational numbers can be written as fractions because they have decimals that either stop or they go on forever in a pattern. But this is a new kind of number that we've never needed before, but we need this number to solve this kind of equation. The area of a circle requires an irrational number. So this is called, this is real, of course. This is a real number, right? I can hold it in my hand, of course. It's a positive number. I'm going to put POS for that. But it's a new kind of number called an irrational number. And that means I cannot write that as a fraction. There is no way to write pi as a fraction. You may think, well, I should say, there's no way to write pi as a fraction of whole numbers. You can't write it as 22 over 7. Some people say pi is 22 over 7. That's just an approximation. It's not the true value of pi, right? But this is not the only irrational number that we've discovered. We have tons of irrational numbers. We have, let's talk about another equation. What about x squared is equal to 2? This is another kind of equation. How do I solve this equation? I'm going to take the square root of both sides, right? So that means I'm going to say that x is equal to plus or minus the square root of 2. We've learned about that. And if you take the square root of 2 and you stick it in your calculator and you look at the decimals, there is no repeating pattern to the square root of 2. It's an infinite number of decimals, numbers that go beyond the decimal, but there is no pattern. Just like pi has no pattern, it is an irrational number. We cannot write the square root of 2 as any kind of fraction. So plus square root of 2 or minus square root of 2, let's say, well, we could just say the square root of 2 is real, positive, and irrational. I'll put IRR for that. And negative square root of 2 is real, instead of positive, it's negative, and it's also irrational because you cannot write it as a decimal. All right? And just in case you're curious, the square root of 2 is something like 1.412135 ... It does not repeat. It goes on and on forever and ever. We can calculate them. Now, why am I going through this trip down memory lane? I think you can probably figure it out, right? The reason is because all of these different kinds of numbers that we have in math were invented at some point in time to solve certain kinds of equations that we needed to solve. The real positive numbers were used when we needed to solve that equation. The real negative numbers, we had to invent a negative number to solve this kind of equation. We needed to understand the idea of a fraction in order to solve equations with fractions. We call them rational numbers. And then we had to have irrational numbers to solve certain kinds of equations that we have outlined here. Decimals that go forever, that you cannot write the number as any kind of a fraction. And now we're taken to the very famous I, the imaginary number. We invent the concept of I because it is useful to solve certain equations that require I as a solution, that require the square root of negative numbers. That is the reason why we have I, because we have to have it to solve certain kinds of equations. And these equations that we're going to learn in algebra, we're going to solve tons of equations that have I as an answer, right? You're going to get them, you're going to circle them, you're going to say, great. But the truth is, we use I probably more than almost anything else in math and higher level learning to solve all kinds of things. Quantum mechanics, advanced physics and chemistry, almost always the solution to very common equations in advanced math actually use the concept of I in the solutions. And I'm going to talk more about that at the very end, where I'm going to give you a concrete example of that. But the idea is we invent this concept of I to solve equations. What kind of equations do we need to solve, right? Let's solve this equation. Very simple. I'm just going to put it to you like this. What if you have the equation x squared is equal to negative 1? How do you solve that? Well, in the previous lectures, we would have just taken the square root of both sides. That's exactly what we're going to do. We're going to say that x is equal to plus or minus the square root of the right-hand side, negative 1. But then we say, well, we don't know how to take the square root of negative 1. There is no real number that actually can be multiplied by itself to get me negative 1. So up until now, we just stopped and we said, well, we can't do that. It's undefined. But in higher math, which is where you're at right now, we don't say it's undefined. We say there's a new kind of number to solve this equation, just like we needed those new kinds of numbers to solve those equations. And this number is called the imaginary number. So we don't stop there, right? We go further and we say, let's take another equation. X squared is equal to -4. We do the same thing. We're going to take the square root of both sides. We say x is equal to plus or minus the square root of -4. In the past, we would have stopped there. We would have said, well, we don't have any answers. We're going to stop. It's undefined. But now we go further. We say that really x is equal to plus or minus the square root of -1, which we're defining to be I. So we say plus or minus I. That's the answer to that equation, right? Over here, we're going to do a lot more problems here. What we have here is the square root of -4. You can kind of think of, we know how to take the square root of 4. That's just 2, right? But the square root of the -1 is still in there. When we take the square root of that, it's I. So it's really 2I, and we still have the plus or minus. So you see, the punchline is when you take the square root of negative numbers, you take them ignoring the negative sign. You just pretend the negative sign's not there. You just write the number down, just like always, but then you tack an I on there because the negative inside of it produces an imaginary number. So this is not a real number. You cannot have 2I potatoes. You cannot have 6I strawberries. It's an imaginary number. It doesn't exist in a tangible form that you can touch. However, as I've mentioned before, if I have 4I potatoes over here as a solution of some equation, I may have to multiply it with some other number of potatoes over here. When I can multiply those imaginary numbers together, I get a real number back. Because when you square I, you always get a real number back. You get -1. That's why imaginary numbers are useful. We say they don't exist initially, but now we say, hey, we're going to define an imaginary number. We're going to keep track of them. But then sometimes they'll combine and give us real numbers back anyway. All right, now what I want to do is solve some very simple additional problems to give you practice actually taking the square root of negative numbers. And then at the end of the lesson, I'm going to do a little bit more into the philosophy of why imaginary numbers are useful for modern day stuff. So stick with me till the end and we'll get there. Let's solve some additional problems. Let's go over here. Let's say we have the square root of -9. As I said, you just ignore the negative. You pretend that it's the square root of 9. You already know what that is. That is 3, right? And you know what the square root of -1 is. That's just going to be I. So let me just take it a little bit more step by step. If you take the square root of the negative inside, kind of pull it out and take the square root, you're going to get the I of the -1, but you'll still have this square root of 9 left over. So this is equal to the I. That I comes about because we're taking the square root of the -1 in there, poof, it turns into an I. But the square root of 9 is still left over, which you all know is 3, so you can write it as I times 3 if you want, but the way we write imaginary numbers is we always put the number first. So we say that the square root of -9 is 3I. So what you do is you take the square root of the number, and then anytime you have a negative there, you just have to tack an I at the end. That's all you do. It's extremely, extremely easy to work with imaginary numbers. So let's take some more rapid fire examples. Square root of 49. You know what the square root of 49 is? It's 7. But you have that negative, so you have to take the square root of that too, so you get 7I. That's the final answer of this problem. This is the final answer of this problem. What if I have the square root of -36? I think you can see the pattern here. We know that 6 times 6 is 36, and the square root of -1 there is the I. So that's not a real number. This is an imaginary number, 6 times the base number that we call I. What about -100? We're going to take the square root of this. Well, we know how to take the square root of 100. That's 10. And the square root of the negative there means we have to put an I there, so that's a 10I, right? Now we learned, up until now, we've learned how to take the square root of much more complicated things than these simple things. We've learned how to take the square root of things like 24. But what if you had the square root of -24? So what you're going to do is you're going to completely ignore the negative sign in there. You're going to come over to the side of your paper, and you're going to write that 24 down and build a factor tree like always. You're going to ignore the negative. So for 24, you know that 8 times 3 is 24. But you know that 8 is 2 times 4. And you know that 4 is 2 times 2. So you got your tree built. You're looking for square roots. So that's a pair. I still have a 2 and a 3 left over, right? So what you have is, when you write the answer here, the square root of -24, you just pretend that the negative's completely gone. And so if there was no negative there at all, I would take a single 2 out. I would have a square root of 2 times 3 is 6, right? I would have that left over. Let me write it explicitly. On the inside, It would be 2 times 3 left over. However, because I took the square root of that negative, I still have an I here. We don't usually write the I after the radical. I mean, it's all multiplied. It doesn't really matter if you put the I here. We put it in front of the radical to keep it away, because if you put the I at the end, you might accidentally leave it under the radical, and you don't want that, right? Imaginary numbers do not live under the radical in general. So 2i times the square root of 2 times 3. So it's 2 times I times the square root of 6. This is the answer to this problem. So whereas before, we don't know what the square root of this negative 24 is, here you can see all we're doing is we're writing the square root as if it were positive under the radical, but then tacking an I on because it's an imaginary number. So working with these imaginary numbers is exceedingly easy, right? What if you have the square root of negative 5? Well, we can't simplify the negative 5. There's no factor tree that's going to help us. But we can take the square root of this negative 1 in there, so that comes out as an I, but what's left over is what's underneath this. The square root of 5 is left over. Just like we had a leftover 6 here in our answer, we have to leave it as a square root there as well. So at the end of the day, you should never ever have negative numbers under a radical. If the only thing you do is just pull the negative 1 out as an I, then that's fine. Can't do anything else with the 5, leave it there under that radical. What about the square root of negative 12? Right? Same sort of thing. You pretend this is a positive number, you go over here, or I guess you could go underneath if you want, but just ignore this. When you build your factor tree, ignore it. You can say 6 times 2, and 6 is 3 times 2. You're looking for pairs, so there's your pair right there. So if there were no negative number there, the 2 would come out, and then underneath you would have a square root of 3, which is left over, but you still have the square root of this negative 1, which means an I comes out. So it's 2 times I times the square root of 3. Now on this page, what I have done is I have tried to show you a basic idea about how to take square roots of negative numbers. So you just do the factor tree as usual, and if you have a negative under there, you just tack an I on. Extremely simple, all right? But we also learned another property of this imaginary number. Because it's defined this way, the I squared, the I times itself is not imaginary anymore. It's equal to a negative 1, which is a real number. So anytime in an equation you see an I squared, then in the very next step you just substitute negative 1. You don't have to think about it. You don't have to derive it or calculate it. Anytime you see I squared, you just write down negative 1. So because of that, we can do some simple problems here. So let's just get some practice. The simplest one is, what is I squared? You just replace it with negative 1. You don't have to think about it. You don't have to prove it. What if I have 2 times I squared? Well, the 2 is totally normal, but the I squared is negative 1. So you just substitute for I squared negative 1, and the answer to this is negative 2. So you see what I mean, how you have 2 imaginary numbers multiplied together, but at the end of the day, you don't get an imaginary number back. You get a real number back, right? Same thing we got here. What if we have 3i wrapped up inside of a parentheses and that whole thing squared? Well, we treat it as we do anything. You pretend this is kind of like a variable. The exponent will apply to the 3 and to the I separately. So you'll have 3 squared times I squared. The same rules of algebra apply to complex numbers, to imaginary numbers. 3 squared is 9, and you're still going to have this I squared. But anytime you see an I squared, you substitute negative 1. Anytime you see I squared, you just put negative 1 there. So it's negative 9. This is the final answer. So when we have 3i quantity squared, we get a real number back, which is negative 9. Now, it turns out that these imaginary numbers, if you have them in a fraction, they can cancel just like variables can cancel. So for instance, 4 times I squared in the numerator with I on the bottom, right? So I'm going to rewrite it just so I don't clutter up my problem statement. So this is 4i squared over I. So if these were variables, if this was like 4x squared over x, what you would do is you would say, well, I'm going to cancel this one, and I'm going to cancel with this one. I'm going to leave an exponent of 1 left behind. Basically, I'm dividing away one of them. And the same thing is true of imaginary numbers. So I had an imaginary on the bottom and imaginary squared on the top. All I'm left with is the 4 and the I in the top. To the first power, it's basically gone, divided away in the bottom. So I get an answer of 4 times I. Okay. What if I have something more complicated? What about 5 times I quantity cubed? But on the bottom, I also have an I. How do I handle that? Well, I still have this numerator. 3 is going to apply to the 5 as an exponent. It's also going to go in and apply to this I, right? So you have 5 cubed times I cubed. And on the bottom, you still have this I, right? But notice that I have the same variable, just like it's not a variable, it's an imaginary number, but you can treat it as a variable. That could cancel with this, leaving me 2. behind. So what I have left with is 5 cubed. 5 times 5 times 5 is going to be 125, but what's left over is I squared. But we now know that I squared is very easy to remember. Anytime you see it, you just replace it with a -1. So what you have is -125. So this whole expression, which looks very complicated with imaginary numbers everywhere, actually is not imaginary in the end. This is one of the things I've been trying to harp on to tell you, is that oftentimes when you're working with imaginary numbers, you'll get real numbers as your answers. The last one I'm going to do for you is a really interesting one. What if you have I cubed? Some students will look at that and say, I have no idea. You didn't tell me what I cubed was equal to. Until you remember that I cubed can be written as I times I squared. Why? Because you can treat it as a variable. I can add these exponents, so of course it's equal to this, and I know that this I squared is -1. So really it's I times -1, which means it's going to be -I. So the imaginary number I can be positive, it can be negative, it can have fractions involved, decimals involved, that's all fine. It's just a placeholder for the square root of -1. And anytime I see an I squared anywhere, I have to replace it with the real number, which is -1. Now I've talked at great length, or at least in the introduction, to try to give you some motivation why imaginary numbers are so useful. What usually happens is you study imaginary numbers in algebra, and then in pre-calculus you do more with it, and then in calculus you do even more with it, and then when you get in really advanced math beyond calculus, you take advanced math classes where we solve special equations. Doesn't matter what they're called. They're called differential equations, but that's the name of them. But anyway, they're equations, and you deal with imaginary numbers every day. And then finally at the end, you understand why they're so useful and how common they are and how real that they are in the solutions of our mathematics, right? But I want to short circuit that because I don't want you to wait 6 years to figure out, or 7 or 8 years to figure out why they're useful. I'm going to give you a quick 10 minutes or 5 minutes explaining that to you, okay? So I've talked about, in general, the idea that I can have an imaginary number, like I have I strawberries. And I can have another imaginary number in my other hand, another I strawberries. So individually, this is an imaginary number, and this is also separately an imaginary number. But when I multiply them together, they form I squared, which I know is equal to -1. So this is one of the main reasons why they're so useful, because separately they're not real numbers, but when I combine them together, they can give me a real number back, which is a tangible thing. This is something I can touch in the real world. I mean, yeah, it's negative, but it's still a number that exists in our everyday, life. So we can get, as a result, a real result. Now, this isn't too exciting. The I times I and all that, it's not too exciting. But there's one example I'm going to give you that's way beyond the scope of an algebra class, but I want to give it to you because it is so powerful for you to understand how common imaginary numbers are in real world problems. I want to give it to you. I don't want you to wait until your second year of college to see it. All right. I want to introduce something to you that we're going to get to later in this math class, in this algebra class. I want to talk to you about something called the sign of some number, right? So the sign. We're going to get to this in algebra later on in our set of lectures. I'm going to explain this to you in a future lesson. So this is not something crazy that you're never ever going to see. This is something quite common that you learn. So the sign is a special function. It's a very special function. Sine of x, this is the x-axis and this is the sine of x. It's very special because it has this wavy shape to it. So it goes like up and then it goes down and it goes up and then it goes down. And on the other side, it continues the other direction. It goes down and up, then down and so on. So you can see it's this general wave shape, right? That you recognize, okay? Why is this important to study this thing called a sine? Why is it so important to study something that has a wavy shape? Well, I'll try to explain it to you. Light, we'll get into advanced physics much later, but light, one theory of light is that it behaves like a wave, right? What kind of wave? Here it is. This is the kind of wave that a light wave actually is. So later on in your education, when you write down what does a light wave look like or what does a light wave behave like, you're going to write down a sine. Or you might write down its cousin, which is called the cosine. I'm not going to get into that because it's the same shape. A cosine is the same shape as a sine. It's a wavy shape, a very special shape that's extremely common in nature. All light waves are sine waves, right? Which means X-rays, gamma rays, infrared, visible light, the light that goes into your eyes, microwaves that you heat your food, radio waves, which your cell phone uses and your walkie-talkies to talk to people. All of those things are sine waves. right? So I'm building it up for you because of the following thing. This sine wave is numbers that are plotted on the y-axis here as a function of this. It's just like any other function. It just goes up and down and up and down and up and down. It can be proven in advanced math classes. It can be shown. I'm not going to show it here because it's way beyond the scope of this, but it can be shown that this thing that we call the sine can be written like this: equals e to the I times x minus e to the negative I times x, all divided by 2 times I. This is incredibly important for later mathematics. It's not important for algebra. I don't care if you remember this. I don't care if you toss it in the trash can and just forget about it. That's fine. What I'm trying to show you, though, is notice what you have here. E is just a number. We're going to talk about E actually not too much longer from now. That's a number. It's a number like pi. It's an irrational number that's very common in nature. It's not equal to pi. It's equal to about 2.7 and some infinite number of decimal places after that, but it's just a number. So this E is not a variable. It's a number. It's some number to the what? To the power of ix. So to an imaginary power. So this is an imaginary power. This is an imaginary power too, but it just has a negative sign in front. So if I take this guy to this imaginary power, and then I subtract e raised to the exact same thing, but to the negative, a copy of itself, but to the negative imaginary power, if I take the answer to that and I divide by 2 times I, which is another imaginary number, see, I'm putting these imaginary numbers in a pot, and I'm stirring them around in this function. What you get out is not an imaginary function. It's a real number. So imaginary numbers go in here, imaginary numbers go in here, imaginary numbers go in there. What you get out is not an imaginary number. You get a real number back. And that real number is a plot. I can plot this real number as a function of whatever I stick in here. See, this is x. It goes in here. Well, you would put it in here, calculate it all, get the thing, but you don't get an imaginary number back. Why? It's for the same basic reason that we don't get an imaginary number back here. I mean, it's beyond the scope. I don't want to prove it, but basically you can see how you can combine imaginary numbers and get real numbers back. Well, I'm combining imaginary numbers in a much more complicated way, and you're just going to have to take my word for it that you don't get an imaginary number back. So why am I doing all of this? Because when I first learned what an imaginary number was, I thought they were useless. I thought I would just circle some answers for the teacher and be done. But it turns out that almost every equation that we solve in real life looks like some kind of wave. And if it looks like some kind of wave that's a sine wave, then it can be written as imaginary numbers. And so a lot of times you'll get an equation, you'll solve it, you'll get some imaginary numbers in the answer. I might have to take that and multiply by another equation, which has some other imaginary numbers. When they get all mixed together, sometimes what pops out is not an imaginary number at all. It's a real number. And that's why it's so useful. Another example would be quantum mechanics. Way future physics, you'll study that long time from now. All the solutions of quantum mechanics, I shouldn't say all, but most of the solutions of quantum mechanics are all waves. They all involve these signs, or they involve these exponents with I in there. And you mix them around and oftentimes you get real numbers back, right? That is why imaginary numbers are so useful. We don't know how to take the square root of -1 with a real answer, but as a placeholder, we just say it's equal to I. We keep it as a placeholder and we start combining it with other things, and then oftentimes, poof, the imaginary numbers go away and we have a real answer back. So it's very, very tangible. When you get to more advanced math, a lot of your answers will be imaginary. You'll get very used to it. They won't seem crazy or weird. And then often they combine back into real numbers anyway, which we can measure in the real world. That is why imaginary numbers are useful. So make sure you understand this, and then follow me on in the next few lessons. We're going to learn how to work with imaginary numbers a little more detailed than we've done here. We'll get a lot of practice by solving problems. Learn anything at mathandscience.com.